Welcome. Today we are going to discuss the chapter of electric current. And the way I'm going to do it is again by doing a quick analysis of this chapter and then by solving problems, right? So when I look at JEE mains, the number of questions that appear from this chapter have consistently increased, right? In 2014 there was just one question asked, and in 16 there were two questions asked, and in 17 and 18 there were three questions from this chapter, right? And the questions from this chapter are relatively easy to solve in my opinion, because there are very rigorous methods to solve problems of electric current. So I would never recommend you to leave a question of electric current if you have solved enough questions. When I talk about JEE Advanced, almost 1 to 2 questions come from this chapter. In 2017 there were 2 questions, in 18 there was 1 question, and 14-15 there have been 3 and 2 questions. So you can expect at least 1 question in JEE Advanced, right? So in this question, I have a finite square grid with each link having a resistance of 40 by 7 ohm. And there's a circular loop which is surrounding this grid, and that is resistance-less. There's no resistance in that loop. And we are required to find out what is the equivalent resistance between the point A and B. When I look at this problem, this feels like a weird electric current problem with and looks really strange, right? How would I solve this problem? Now, the first thing I notice here is that the circular wire here is a resistance-less wire. That means that this point over here is at the same potential as A, and the same thing is with this point over here, and the same thing is with this point over here. So all the corners of this grid are at the same potential, right? And that is the same potential as A, because they are all connected by a resistance-less wire. So when you have 2 points in a circuit which have the same potential, no current will flow between those 2 points, right? So it's as if like those 2 points are basically the same point. Current has no motivation to go through it, right? So current flows only when there's a potential difference. So I can, call this point also A, this also A, and this also A, because they are basically the same point. Okay. Now when I look at this circuit, with having done this, now I can see a beautiful symmetry, right? If there's a current which flows through B to A, then you can clearly see that the way the current would spread itself, right, from B would be in a symmetric way, because all other branches which are coming out of B are all symmetric. So let's say if an I current comes out here, the same current will come out here, the same current will come out from this end, the same current will come out from that end, right? And that is because they are symmetric. Why would a higher current come out of one of the branches and a lower current would come out of other branch? There's no reason for that. They're all perfectly electrically symmetrical. So that again makes me realize another thing, that if that is how it is going to be, that each and every point is going to be symmetric, then we can find other points which will be at the same potential. So here I can say, see, for example here, let me call this as point F. So point F, this point, this point, this point, and this point, I'm calling all of them F, because now you can see that they will have the same potential, because whatever is the potential at B minus IR will be the potential of that point. So all these points will be the same potential. So the thing you have to realize is all the symmetric points will have the same potential. So I can call them F, all of these as F. So for example, if I say this is C, all the points symmetric to this point here, 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 this and this, they're all C. They all have the same potential. So if you connected any of those 2 points together, there will be no flow of current because there's no potential difference. Now, are there any other points? Okay, there is this point, let me call this as point D, this here, and this here. They are all of the same potential. So I have got A, C, D, B is already there. Now these are still remaining. So this point here is, if I call that E, the symmetric point here is E. Here I have got E, and here I have got E. Okay, so I have marked out all the symmetric points here, and I'm calling them the same names because they will have the same potential. And that is the concept. I'm stressing on it again and again because that's the most important, the most crucial thing. Okay, now once you do that, you can reduce this complicated looking circuit into a simpler circuit, right? You can see that between A and C, how many connections are there? Between A and C, there's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 connections between A and C, right? And if I want to find out the connection between C and D, how many connections are there? Okay, let's see that. 1, 2, 3, 4, 5, 6, 7, 8. C and D again have 8 connections. Now, what are the number of connections between C and E? So C and E, how many connections? So 1, 2, 3, 4, 5, 6, 7, 8. So between C and E there are 8 connections. Now let's look at D and F. How many connections are there between D and F? So between D and F, so this is 1, 2, okay, this is 3, and this is 4. There are 4 connections between D and F. Similarly, I can find connection between E and F. So E and F has how many connections? E and F has this 1, 2, 3, 4, 5, 6, 7, 8 connections. And similarly, there are connections between F and B. So this is 1, 2, 3, 4 connections. Okay. So once you draw the circuit, okay, so first thing is you found out all the points with the same potential, you called them the same names, and then you drew an equivalent circuit for this thing. And once you do that, you can see that the resistance between A and C, all these resistances are in parallel, and each of them have a resistance of R. Okay, let's just call it R for now. The value of R is given to us as 40/7. We'll use it in the end. So what will be the equivalent resistance? There are 8 of them and they are in parallel, so this will become R by 8. So between C and E, this will become again R by 8. Between C and D, it will become R by 8. Between D and F, there are 4 of them, so it will become R by 4. Between E and F, it will be R by 8. Between F and B, it will be R by 4. Okay. So once you reduce it to this, now you know that this is cakewalk, right? You can solve this like any day. So between C and F, what will be the resistance? So R by 8 and R by 8, they are in series, so this becomes R by 4. And on the other end, you have R by 8 and R by 4. They are again in series, this will become 3R by 8. Now this 3R by 8 and R by 4, they are in parallel. So 3R by 4 into 3R by 8 divided by R by 4 plus 3R by 8. This is the formula we use when we have 2 resistances in parallel. This becomes equal to 3R by 20. Okay, so this whole thing is 3R by 20. So now this 3R by 20 is in series with R by 8 and R by 4. Okay, so you just add R by 8 plus 3R by 20 plus R by 4. When you do that, you get a result which is equal to 21R by 40. Okay, and the value of R is given to us in the problem to be equal to 40/7, and 40 gets cancelled. Anytime I see that there's a number which gets very easily cancelled, cut off when an expression is given, I know that I got to some the right answer, because see 7, 21 is a multiple of 7, so 7 becomes 3, so this becomes 3. So the answer is a good pure number 3, and that's the right answer. So in this problem, there are 24 cells, and each cell has an internal resistance of 1 ohm, and they are arranged like this. There are y number of these internal resistances which are in series, and there are x such rows. Okay, and this whole setup is attached to an external resistance of 10 ohms, and basically we have to find what should be the value of x and y so that there is maximum power delivered to this external resistance. So when you have a setup where you have an EMF, let's say an EMF E, and an internal resistance to that EMF, say R, right, this setup, and then it is connected to an external resistance, say capital R, and you need to know what should be the value of this capital R so that there is maximum power delivered to it. Here our problem is different. Our problem is the external resistance is fixed, and we have to find out what would be the internal resistance setup so that the power is maximum. So usually this is the case which is given in most of the books and which is taught, and that result says that power delivered will be maximum when R is equal to R. So when the external resistance is equal to the internal resistance, the power delivered is maximum, right? So in this case, I have to somehow find out the net internal resistance and then set it equal to capital R, which in this case is 10 ohms, and in that and doing that should make me arrive at the expression or the values for x and y. So how would I do that? So let's first find out what would be the internal resistance in this case, right? So there are y number of resistances, 1 ohm resistances, which are like this. So I can say that the total resistance in one of those rows will be y times of R, right? And how many such rows are there? There are x number of rows. So if you have 2 rows, the total number of resistance will be yr by 2. If you have 3 rows, it will be yr by 3. So in this case, it will be yr divided by x. That's the total internal resistance, right? And if I add it to the external resistance, this is the total resistance in the wire. And total EMF, how much will it be? So EMF in each row, if you see, there are y number of batteries or y number of cells. So y times E is the total EMF in each row, right? And the potential difference across one row is the same potential difference across all the rows, right? So net EMF across any 2 points, if you take at the end of any row, is y times E. And it doesn't matter how many rows you have, because potential difference between 2 points is going to be the same, right? So that point is similar to that point, and this point is similar to this point. So the potential difference or the EMF is going to be the same, y times E. So what I have done here, if I have written an expression for its current, I is equal to YE divided by YR by X plus R, alright. So I have told you that power will be maximum when the internal resistance, which is this expression, will be equal to the external resistance, which is this. So YR by X must be equal to R, right? And that will give us the maximum value of power. So here the value of small r is 1, capital R is 10. So this becomes Y by X is equal to 10, or Y is equal to 10x. So if Y is equal to 10x, you would get the maximum power. This is the expression for maximum power. Okay. There's another relationship between X and Y, because it is given in the problem that the total number of cells are 24. So we have X times Y is equal to 24. Okay. Y number of cells and X number of rows. So X times Y will be the total number of cells, or total number of resistances, you can say. So X times Y will be equal to 24. Alright. Now let's use these two expressions to find the value of X and Y. There are two variables, two expressions, we can do that. So when I do that, I can plug Y as 10x. So I get X times 10x is equal to 24. That makes X square equals to 2.4. And that makes X to be equal to root over 2.4. And root of 2.4 is how much? When you calculate that, you find this is equal to or close to 1.55. Okay. Now X is the number of rows, right? It cannot be 1.55. How can you have 1.55 rows? You can either have 1 row or 2 row, right? So the value of X can either be 1 or 2. It cannot be this perfect value. If it were this perfect value, which is not physically possible, then the power would have been maximum, right? But it can't be. So let's see the numbers which are close to it, the whole numbers which are close to it, right? So let's take X is equal to 1. When X is equal to 1, from this expression, which is the actual mathematical expression that we got here, this was the expression for maximum power, which is not applicable anymore because it gives us the wrong result. So for this, in this expression, when I plug X is equal to 1, I get the value of Y equals to 24. Okay. And if I take X equals to 2, I get the value of Y equal to 12, right? If X is equal to 2, Y will be equal to 12. Now let's use this, let's call this case 1 and call this case 2. Okay. If I see for case 1, alright, what would be the power? The power is defined as I square times R. This is the power again across the external resistance. So this will be equal to I is YE, right? So your Y is 24 in the first case, 24E divided by 24 times R is 1 divided by the value of X in that case is 1 plus the value of external resistance is 10. Okay, so when you find this, you get this expression equal to close to 5 times e square, right? And in the second case, when you find the power equals to I square r, so value of I will be ye. Again, I'm using this expression, so that is 12 times e divided by 12 times 1 divided by x, which is 2, plus r again is 10. This expression comes to be 5.6, close to 5.6 e square. So I can see that in the second case, the power is maximum. Okay, and in the second case, if I so this is the way you solve this problem. And the way I just solve this problem is actually a long way to solve this problem. There's also a short way to solve this problem. The short way would be, so if I had to actually solve this problem in an exam and not care about teaching it to you, let's say, so you have yr by x is the internal resistance, right? And I find that the value of x is 1.55, so it can be either 1 or it can be 2, right? So when I put x is equal to 1, value of y becomes 24, so I get 24r as my internal resistance, which is equal to 24 ohms, because the value of r is 1. So when I put x is equal to 2, I get y is equal to 12, and the value of internal resistance that I get is 6 ohms, right? So this will be 12 by 2 times of r. If you do this, that's easy. So you get 6 ohms. So I know that when internal resistance is exactly equal to the external resistance, the power is maximum, right? So power will be more when the internal resistance is close to the external resistance, right? So when compared to 6 and 24, 6 is closer to 10 than 24. So I would say that the 6 ohm case would give me more power, and so I should take the value of x is equal to 2, right? So that's the easy way. So here the value of x is equal to 2 and the value of y is equal to 12. So if you look at the expressions that we have given, you see that y minus x will become 10. So option B would be the right option. Now here is the first problem we are going to discuss in electric current. So in this problem we have a resistor, and the resistance of that resistor R of t is given to be R0 1 plus 2 gamma t plus phi t square. This is given to us, and we are told that gamma and phi, they are constants, and we have to figure out the temperature coefficient of resistance. Okay, so we have to basically find out the alpha in this problem. Now how would I find alpha? So when I see that I know that when you increase temperature, the resistance of a resistor increases, and there's a relationship. The relationship that I remember is R is equal to R0 1 plus alpha delta t, right? This is the formula. The thing is, this is an approximate formula, and many students don't realize that this is a formula you cannot use everywhere, because this formula has an intrinsic assumption that alpha is not dependent on temperature. Alpha is constant for a while, and this formula works when the temperature range is very small, but it doesn't work all the time. Okay, so which is that formula which works all the time? So that formula it's actually an expression for alpha. Alpha is equal to 1 by r dr by dt. Okay, so this is a general expression for how that resistance would vary with temperature. Okay, and this formula over here is an approximate formula which we derive using this expression. So when alpha is given as a function of temperature, you have to use this formula. Now let's do this. So alpha is equal to this. So here alpha will become equal to 1 by r, which is equal to 1 by r0 1 plus 2 gamma t plus phi times of t square times dr by dt. So d by dt, or they are using small t for temperature, so let me also use that, of 1. So this is R0 times 1 plus 2 gamma t plus phi t square. Okay, and this is what I have to do. So this becomes 1 upon R0 1 plus 2 gamma t plus phi t square, and differentiation of this will be R0, and inside I'll get 0 plus 2 gamma plus 2 phi t, right? Simple differentiation. R0 and R0 would get cancelled. Okay, so this expression would become 2 gamma plus 2 phi t upon 1 plus 2 gamma t plus phi t square, and that's it. Okay, in a matter of seconds you can solve this problem, and this is the right answer. So all this problem wanted to check is whether you know the general expression for the temperature coefficient of resistance. So now I have this question over here. Now this question looks really complicated. It's a multi-answer question. We have got 4 options, and you have to go through the options and see which one of them are correct, which are not. The thing with this question is that it looks complicated, but it is not, because see, whenever you get a question of electric current, the first thing you need to see is can you use series and parallel concepts of series and parallel resistances to solve that problem. And here you actually can. The first question says the equivalent resistance between G and C is 3 kilo ohms. Between G and C, between both those points. Okay. Between G and E, if you see, this 1 ohm, 1 kilo ohm and 1 kilo ohm, 1 and 1 becomes 2, and here also 1 and 1 becomes 2. This 2 and this 2, they are in parallel with each other, right? Please mind that these both 2s, these 2 kilo ohms are not in parallel with that 1 kilo ohm, right? Because for 2 resistances to be in parallel, their ends must meet. That is in the sense to say that the potential difference across them must be same. So I'm not sure whether the potential difference between these 2 resistances will be the same as this. And how I'm not sure is because their ends are not the same. So I cannot say that this will be in parallel. So I'm sure that this 2 and that 2 are there in parallel, and that becomes 1. And now I can see that that 1 is actually in series with this one. This whole thing becomes 2. Okay. Now let's look at this internal square. In the internal square, you see this 1 and 1 again are in series, this become 2, and this 1 and 1 are in series, become 2, and 2 and 2 are in parallel, become 1. So you have 1 from here and 2 from there. So the total resistance, the equivalent resistance, becomes equal to 3 kilo ohm, which is right. So option A is the correct option. Now let's look at option B. It says that the current provided by the source is 4 milliamperes. Alright. So we just found out that the equivalent resistance is 3 kilo ohm. The source has an EMF of 12. So 12 by 3, right, V by R will give you I, which is equal to 4 into 10 to the power of, if you keep that kilo 10 to the power of 3, this becomes 10 to the power of minus 3. So that becomes 4 milliamperes, right? So option B is also correct. So option C says the current provided is 8 milliamperes. So that can't be true because we just found out it's 4. So option C is not correct. Let's check out option D. The potential difference between G and E is 4 volts. Between G and E, between these 2 points, is 4 volts. So to solve that, I see that this circuit has a kind of a symmetry, right? So these 2 paths here, going from G to H and G to F, and then F to E and H to E, they're perfectly symmetrical. So the current wouldn't distinguish between these 2 paths, okay? And all the central mechanism here, the one that connects from E to A, and then all the central thing, they're all purely symmetrical. So if let's say from C some I current flows, that I will come back to G, but it will come in a symmetric way. I by 2 will come from this end, and I by 2 will come from this end. Okay. So I know that I current is 4 milliamperes. So 2 milliamperes must be coming from this branch, and 2 milliamperes must be coming from that branch, right? And if I know that current, then the potential difference between G and E just becomes a question of let's move from E to G, right? So this becomes 1 into 2 plus 1 into 2, that's equal to 4 volts. So the potential difference between G and E is equal to 4 volts. So option D is the right option. So in this question, there's a conductor, and it is said that each atom of this conductor is contributing just 1 electron, or 1 free electron for motion, for the current to flow. The area of cross section is given, the current flowing is given, so I is given to me, all right. The area of cross section is given to me, all right. Length of this conductor is given to me. The density of this conductor is given to me, all right. And the drift velocity of the electrons in millimeter per second is what I have to find out. Then there are some extra information given about atomic weight, and then Avogadro's number is also given, and then the value of the charge of an electron is also given, right? The magnitude of that is given. So now how would I solve this problem? The first thing that clicks to me is the relationship that I have between the current and the drift speed, right? Which is I is equal to NEAVD. Okay, I'm just going to call it Ne, that is the number of electrons, times EAVD, right? This is the formula for current. So current is given to me, this is known to me, area is given to me, this I have to find. I don't know what this is. What is Ne? Ne is actually this variable over here is the number of electrons per unit volume. That's the definition of Ne, right? So number of electrons per unit volume, all right, that is what it is. So what will be the number of electrons? The number of electrons will be equal to the Avogadro number times the number of moles of electrons, right? So if there are m moles of electrons, if you multiply that with the Avogadro number, that will give you the total number of electrons divided by V. This is my value of Ne, okay? So this becomes equal to, now m, if m is the number of moles, what is 1 mole equal to? 1 mole is equal to the given weight divided by the molecular weight, right? So this will become equal to Na times the given weight divided by the molecular weight, which is m, times this V, okay? So this is a bit of chemistry coming up here, but you got to know that, okay? So things can, and a lot of questions in physics sometimes use the mole concept. So mole concept is a very important concept for you to know. Now what do I have to do? All right, so this W by V, right? W by V is actually the weight by volume, which is equal to density, right? Density is given to me, so I can write it as Na D by M, okay? The value of Na I know is 6 into 10 to the power of 23 as given in the problem. The value of density is how much? Density is 5 into 10 to the power of 3, and the molecular mass given is 60, okay? That's it. Now I have to find this. There's one mistake here though, that the molecular mass usually is defined as grams per mole, okay? So here it is 60 grams per mole. We have to convert it into kilograms per mole, right? So that will be 10 to the power of minus 3 will also come here. So when I find this, I get this gets cut here by 10. So this 10, this makes it 10 to the power of minus 2. I take it on the top, this becomes 10 to the power of 5. This becomes 5 into 10 to the power of 28. These many electrons I have per unit, per cubic meter, right? Now, so that's not what I have to find. I have to find Vd. So now let me plug things in this equation, my original equation. So the value of I is 16. Value of N I just found out to be 5 into 10 to the power of 28. The value of E is 1.6 10 to the power of minus 19 into the area is given to me as, when you look at the problem, the area is 10 to the power of minus 6. That's also in SI units, good. Vd is given to me, Vd I have to find out, all right. So let's do that. So, this is easy. So this 1.6 goes with this 16 by 10, okay. This 5 will come here, below 10 will become 2, and 10 to the power 28 minus 19 and minus 6 to 19 plus 6 is 25, and 28 minus 25 is 3. So this becomes 2 into 10 to the power of minus 3 equals to Vd, a simple calculation. So the drift velocity is 2 into 10 to the power of minus 3 meters per second, because everything was in SI units, right? So if it is 2 into 10 to the power of minus 3 meters per second, it will be 2 millimeters per second. So for this integer type problem, the answer would be 2.
For more videos and live lectures on the JEE, click on the subscribe button now.